Professor of Physics in Government Nagarjuna PG College of Science, Raipur, Chhattisgarh. It's my privilege to introduce Dr. Ravindra Kumar Gupta, Sir, Assistant Professor in King Saudi Arabia. Sir has done PhD from Pandit Ravi Shankar University, Raipur, in Solid State Ionic Material Science. Spent more than 25 years in research and academics. Research area of interest is solid electrolytes and electrodes for renewable energy source and batteries. Also in nanomaterial for energy application, more than 33 conferences and 86 plus research paper published. So I would like to invite Dr. Ravindra Gupta sir for his talk. Very welcome, sir. Sir, you can share your screen if it is required.
Can you see it?
Sir.
Yes, sir. दिख रहा है sir. Yes.
Is it okay?
Yes.
Okay.
Sir.
Good morning. I think in India it is morning. Good morning, everybody. Thank you so much to the organizers. As Dr. Mohan and Dr. Ansuman told, my area is solid state ionics. And I'm still working on this area because we have a lot of problems and we want to solve using the solid electrolytes. So, but today I will talk about the solar cells. Being a person of the solid state ionics, because we are using the solid electrolytes for the dye-sensitized solar cells. So I will discuss little about this also. So this is the fundamental things actually. And just like a small review. And I'm also learning actually because of Mohan. He told me about solar cell. So I told, okay, I will try. And so I prepared the these notes, this presentation file. So I'm also learning with all of you. So this is the my content of the talk, sunlight, solar cells, and then I will talk about the different types of solar cells, and then about the confirmed solar cell efficiencies. So sunlight, what is sunlight? This is the source of energy. This is a type of renewable energy resources which is available plenty, and this is the actually it comes from the sun. So we say sunlight, and it is a part of the electromagnetic wave spectrum, and it is from the 400 to 700 nanometer. We also have ultraviolet as well as infrared. So if you see this sunlight on our earth, so you can you can see here, this is for the this is for the black body radiation on our earth. And then this is the sunlight, that yellow color sunlight without the atmospheric absorption. At the sea, you can see this is the red color. So we want to utilize this light in the visible region, if possible in the infrared region and UVA region. So this is the target. And you can see here we have different standards. So we use AM 1.5G, means with angle 48.2 degree for the solar cell application for standardization. So this is the thing. And this is the world solar energy map. So if you see, if we are on the Tropic of Cancer or on the Tropic of Capricorn or in between these two, we have high sunlight irradiance. It's very, very high. And for the Saudi Arabia, for example, for India, for Tunisia, and in Sahara Desert, actually in USA, like that, we have so much irradiance. So it is 2 megawatt per hour, 2 megawatt hour per meter square. It's quite high. So we want to utilize this sunlight irradiance. So we have one device known as the solar cell, which is also known as photovoltaic cell. And this is a type of renewable energy sources. So what are the advantages? Here we have sunlight as a fuel, which is widely available, accessible, infinite. So no emission, no combustion, no radioactive waste. See, this is the advantage. Because fuel is free, so no, low operating cost. It has no moving parts. We can operate around in the ambient condition, means maybe 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius, no problem. High reliability of solar modules. Manufacturer guarantees over 30 years if you have the silicon-based solar cells and gallium arsenium based solar cells. Rather predictable annual output. Modular can be small as well as large. Any kind. We can make any size, no problem. Can be integrated into new or existing building structures. Like that, it has so many advantages. But it has some disadvantages also. It is intermittent. The sunlight is intermittent. Okay. And fuel source is diffused. Okay. Density is less. High initial cost. At the beginning, we have to put a lot of money. And if we have the silicon-based solar cells, we get back our money within 3 years. But for the Dyson-sized solar cell, it is less than 1 year. Unpredictable hourly or daily output. Of course, for the year, we can predict, but for the daily basis, we can't do it. And efficiency is still not so good, and storage is a big problem. These are the basic problems we have. So what is the basic for the solar cell? So if we have any semiconductor material, so there we have one valence band and then conduction band. And because of the, if we have photon, which has energy greater than the band gap energy of the semiconductor, then because of the absorption of the photon, this electron get excited from the valence band to the conduction band, and then this electron migrates through the external load and gives the power to the device. So this is the basic thing, basic physics actually. But what are the solar cell materials? Which type of solar cell we choose? So the basis is how well the absorption characteristics matches with the solar spectrum, and also the cost of the fabrication. So these are the two requirements for the solar cell materials. So we have different types of solar cells. Silicon nowadays available everywhere. We have third, fifth elements based solar cell, chalcogenide, quantum dot, sensitized solar cells, organic solar cells, perovskite solar cells, Dyson-sized solar cells. And I will discuss little more about the silicon-based solar cells, because this is the base of our solar cell. Then we have different type of solar cells. And being a person of the solid state ionics, we are utilizing the solid nuclide for the solid state Dyson-sized solar cell. So I will try to discuss if I have time. So silicon-based solar cell first. Why silicon? This is the question. Silicon is abundant. You know it. It is abundant. Everywhere we have. In terms of the sand, SiO2. absorption characteristics of silicon matches fairly good to the solar spectrum. Here you can see band gap energy is around 1.12 electron volt. This is very, very good. Silicon fabrication technology is well developed. As I told earlier, quantity is abundant, non-toxic, environment friendly, and this is from the fourth group. Okay. And when we add the third group into the fourth group, we have p-type material because of the holes as a majority charge carriers. And when we add fifth group element into the silicon, we have n-type material where electrons are the majority charge carriers. So if we make a cell like this, here you can see this is the p-type layer, this is the n-type layer, and then we have the pyramid, inverted pyramid structure as an anti-reflective layer, then metal grid to collect the current. Here we have the base, back surface field, metal contact. So when we have sunlight irradiation, because of the electron hole formation, we have the current, and which passes through the this metal grid, comes to the passes through the load and comes to the metal contact. So this is the basic thing. So here there's one thing I want to say you. This is thick. It is around 300 micron. This is around 0.35 micron. Okay. So this is the basic phenomenon. Because of the PN junction, we have the depletion region, also known as space charge region. Here we have no free electron and holes. Here we have electrons in majority and holes in minority. Here we have holes in majority and electrons in minority. So what happens when we have the radiance of the sunlight? We have electron hole formation everywhere, but useful is in this section, in the depletion region. So this electron migrates toward the this grid, and this hole migrates towards the this side. Okay, and then we have electron migration from through the load. So this is the basic, as I told you earlier, this is the basic thing. And we have recombination also, 3 types of recombinations: single level trap because of the impurities, radiative from valence band to conduction band, from the conduction band to valence band. Then we have the agar type of recombinations also, which actually recombination is not good at all. So we have to reduce the recombination. And this is the model. So we have 2 types of recombinations. One from the N-type region and P-type region. Another is from the depletion region. So I01 from the N-type and P-type region, and I02 from the depletion region. So it generates dark saturation current, and thus the recombinations. So we have, this is the expression for the current, total current. This is the open circuit voltage. When we have no current, then this is the open circuit voltage, which is the function of ISC and I011 also, and it depends on temperature as well, you can see. So here, this is for the model. Here, if you see, thickness is for the N-type region, 0.35 micron. For the P-type region, it is 300 micron. And doping density is here, it is highly doped. It is 10^20 centimeter per cube, centimeter cube. And this is the 10^15 surface recombination is, it is, you can see low, but here is very, very high. Minority charge diffusivity is here very high, but here low. This is the advantage of the BSF, the your back surface field. And the lifetime of the minority carrier should be less in the N-type region and high in the P-type region. So we have that thing, and the diffusion length should be lower in the minority carrier in the N-type region, and it should be high in the P-type region. So these are the basic requirement. This is the characteristic solar cell. This is the solar cell characteristics IV curve, and you can see it is flat. If it is ideal condition, you can see it is just like a box like this, but in the actual case we have like this. So here we have three parameters: ISC, VOC, IMP from this point, VMP from this point. So here we have three parameters to get the efficiency, fill factor, ISC, and VOC. So, and fill factor depends on the, this is just a ratio of the VMP, IMP divided by VOC, ISC, and efficiency, you can see. And in general, we measure the efficiency at 1000 watt per meter square or 100 milliwatt per centimeter square. It is known as 1 sun or AM 1.5G. This is the standard condition as I defined earlier. But that is the ideal condition. We also have the resistances, and this is the current. You can see we have two types of resistance. First, the series resistance due to the movement of the charge carriers through the emitter to base of the solar cell. Contact resistance between the metal contact and silicon, the resistance of the top and rear metal contacts, as well as wires also, leads also. And because if we have high series resistance, you can see fill factor is very low. So the series resistance should be as low as possible. It should be 0. Okay. So if we have 0, then we have very good efficiency. So this is the thing. And then next is what happened? Hello. Hello.
Yes, sir, you are audible.
Okay, it's got stuck actually. Okay, now working. And then we have the shunt resistance. Here you can see the shunt resistance should be, this is the shunt resistance. It should be as high as possible. If it is low, you have the current will pass through that low resistance. So it should be as high as possible. It should be infinity actually. So what happens when we have the low resistance? So in this case, the current diverges from the shunt resistance and reduces the voltage, and also reduces the current. So which is not good at all. So actually this is due to the manufacturing problem. This is the manufacturing problem, not from the solar cell design. Okay. So these are the parameters. What is the effect of temperature? So when we increase the temperature, we increase the intrinsic concentration and also increase the dark saturation current because of recombinations. So it reduces the open circuit voltage. Means high temperature is not good at all. For the silicon-based solar cell, temperature should be low. Low means it should be in the ambient condition. Maximum 40 degrees Celsius, not high. But in Saudi Arabia, temperature is very, very high. 50 degrees Celsius, several places. So it's not so good. That's why dye-sensitized solar cell is very, very good. Higher temperature, higher current, higher open circuit voltage for the dye-sensitized solar cell. And this is the limit. If you see for the PN junction diode, for the black body radiation, you can see here, it is A, unconcentrated. So it is around 30%. For the full concentrated, it is around the B, it is 40.7%. For the AM 1.5G, it is around 32%. This is the limit for PN junction. So we can get the highest conversion efficiency of 32%. This is our limit for the single junction PN solar cell. And this is for the 1.1 electron volt. So here this is the solar spectrum with wavelength. This is the quantum efficiency. So here you can see it is very, very low because of the front surface recombination. And here we have less because of this is the ideal condition, actually. This is the ideal condition. It should be like this only, but this is not true. Here we have the very, very low because of the front surface recombination. Here we have the reflection as well as the low diffusion length. So we have to reduce the reflection. The loss should be very, very low, and the diffusion length should be high as much as possible. And the red response is due to the rear backside surface recombination, as well as the long wavelength. If we are going towards the infrared, so naturally energy is less. So naturally the photon conversion to electricity will be less. And if it is less than the band gap of the semiconductor, naturally no conversion. So what are the key factors to design a solar cell? So here you can see N ideal means the semiconductor materials of the band gap of the semiconductor material should be matched with the solar spectrum. Means it should be around this region, 1 to 0.75, not 0.75 actually, around 1 electron volt to 2 electron volt. This is the condition. Optical losses should be as less as possible. It should be very, very low. Okay. So there should be no grid shadowing, no reflectance, no absorbance. Okay. So it will and the maximizing the optical thickness of the solar cell. Okay. Another thing is the series resistance and shunt resistance should be low, and therefore the fill factor will be high. And minimizing the bulk and surface recombination rates, so it will increase the open circuit voltage as well as short circuit current. So these are the parameters to improve the solar cell efficiency. So now I'm going to talk about the amorphous silicon-based solar cell. This is the configuration. Here you can see this is the glass. I have 20 minutes left. So this is the glass. On that we have the front transparent conducting oxide, which is either ITO, indium doped SNO2, or aluminum doped zinc oxide. Then we have P-type material, which is very thin. You can see here. And this is the amorphous silicon carbide or microcrystalline silicon hydrogenated. And then we have intrinsic amorphous silicon here. And then we have N highly doped amorphous silicon, or the microcrystalline silicon. And then we have the rear TCO, Then we have back contact, which is made of silver, or nowadays we are using aluminum. So this is the basic configuration for the amorphous silicon-based thin film. And this is the microcrystalline silicon-based thin films. Here, this is the glass. This is the first generation. This is the second generation. So here, this is the, we are using polycrystalline silicon layer because it is cheaper also instead of glass, amorphous silicon. So here you can see this is the back reflector on the glass. Then we have N type of layer, the intrinsic polycrystalline material. Then we have P type of layer. And here we have surface structure. Okay. This is the inverted pyramid style. It acts as a anti-reflecting coating. Okay. So, and then we have ITO, and then we have grid to collect the electron. So this is the microcrystalline structure, thin film, of course. Then we have another structure. So actually in the market at present, we have this type of solar cells. At present, we have amorphous based also, polycrystalline based also. But nowadays, in the market, we have PERC based conditions. So what is PERC? This is the passive weighted emitter and rear contact cell, PERC. What happens? This structure reflects photons back into electron layers, causing the cell to produce more power and preventing electron recombinations. These two benefits result in increased energy conversion efficiency and decreased heat in solar modules. So if we have actually recombination, as you saw, we have photons because of the heat, and which is not good at all. So if we have the recombination, so naturally low heat generation. So PERC helps. So here we have passivation. Here you can see, here we have passivation. Here we have passivation. So this reduces the recombination with the minority charge carriers. Minority charge carrier here as well as the minority charge carriers in the P region. Okay. So this is the cell design. You can see here. This is the front contact made of silver, and nowadays we are using TI also. This is the anti-reflecting glass, SiO2. This is the quartz glass. This is the inverted pyramid style. Then we have the negative N type of material. Here you can see very thin, very, very thin. Then we have P-type silicon layer here. These are crystalline material. Okay. And then we have local back surface field. And then we have a passivation layer, which is made of alumina or SiO2. Then we have dielectric capping layer, silicon nitride. Then back contact made of aluminum. So this is the structure, but it is little complicated. But we can use the manufacturing plant, what we have for the normal solar cells manufacturing system. So, but that's why it is cheaper. We don't need much conditions for manufacturing expensive manufacturing plants. Whatever we have available, we can use. This is the another structure known as TOPCon cells. Nowadays it is also coming, but at present contribution is less. So here, tunnel oxide passivated contact. So what is the, this is similar to your PERC cell, But here you have little difference. This is the ultra thin tunnel made of SiO2. It is very, very thin on the p-doped silicon. This is the polycrystalline. And then we have the aluminum. And then we have the, this is the then N-type polycrystalline material. No, sorry. This is the crystalline material. And then we have highly doped p-type material. And then we have the alumina or silicon oxide or magnesium fluoride. Then we have either silver or titanium or mixture actually. Many times we use Li also nowadays to reduce the cost. So this is the another type known as IBC cell, integrated back contact cell. So this is here you can see it is similar to PERC, but here we have P-type, N-type, like this, alternative, okay, at the bottom only. So here we have no grid. Can you see here? We have no grid. All grids are at the bottom. So what happens, advantages here, we have no shadowing effect, no contact effect, okay? And the series resistance is less, naturally, because all are on the bottom. So this is the advantage. And this is the structure you can see here. This is the N-type material, highly doped. This is P-type material, highly doped. Again, N-type, like that, it has a series, N, P, like this. And in between, you have, this is the silicon oxide. Then we have grid, metal grid. And here, this is the P-type of amorphous silicon. And this is N-type of amorphous silicon. So we are using here amorphous silicon as well as crystalline silicon also, doped silicon. So two things together. So cost is less, naturally. Okay. So here you can see the structure more clearly. This is N plus, this is BSF, this is P-type emitter, N plus VSF, that's metal finger, like that. So both contact layers are at the bottom. So this reduces the contact resistance. So this is the advantage. Next is, it gets stuck actually. I don't know why. Okay, now coming. These are the advantages as I discussed, but there's a complications. The current flow of carry is done in 2 dimensions, but when we use standard cell or PRC, it is one direction only. The efficiency of the IBCL is deeply related to the BSF lifetime and the front surface recombinations, demanding higher quality silicon wafers with a longer carrier lifetime. So these are some complications, but very easy. And the future is on the heterojunctions technology. After maybe 2030, we will be having this more in the market. So here you can see this is amorphous based with the this amorphous and the crystalline based both. So here if you see, it is 2 types. This is the HBC type, heterojunction with integrated back contact. It is IBC actually, heterojunction with IBC structure. This is heterojunction with intrinsic thin layer style. So we have 2 styles. And of course, this is very, very easy, better than your previous one. So this is improving. It has low temperature coefficient, easy to make. So low light in performance also it has. life is more. And now I will talk about the efficiencies available with the in the market. So this is for the crystalline silicon-based solar cells. This is from the NREL, USA. So here, if you see silicon-based solar cell, this is single crystal with concentrator. There's one more thing. If we have concentrator, if we focus the sunlight on the solar cell, we can increase the photocurrent. This is the advantage. But condition is the temperature should be low. So we must have cooling system also with the concentrator. Then only we can increase the current. Otherwise, it will decrease the voltage. This is the problem. So this is for the single crystal. This is single crystal with non-concentrator. Here you can see this is multicrystalline. This is multicrystalline. This is for HJT. Here you can see is very, very high, 24-26%, something like that. And this is from the Green et al. Green, Martin Green actually group records the efficiency, and they publish every 6 months. So this is the latest one, published recently in 2023. So here you can see these are the standard. These are the reported and tested actually. So this is for the silicon-based solar cell. Areas you can see very, very high. This is from the company Longi, N-type HJT. This is 26.8%. But when we have directionally solidified wafer cell, it is 24.4%. But this also area is very, very good, you can see. But for the thin film, this is 21.2. But when we have mini module thin film, this is 10.5%. This is from company CSG Solar. Here, the thickness is less than 2 micron. Okay, the thickness is very, very thin. What about the amorphous silicon? You can see this very, very low, 10%, 11%. And this is for a small area. And when we increase area, it will be further less. What about the other systems? Actually, the best from other groups. So here we can see for area 4 centimeters square, 25%, like that you can see. This is for 244, 24%. So, and for large crystalline, this is 26%. So here you can see it's very, very high, very, very good. That's why silicon-based solar cells are very promising. Everywhere we are using. And the life means we can, lifetime is more than 30 years. It can go maybe 50 years also, no problem. This is the advantage of the inorganic materials. Next is the fifth elements based solar cells. So here we have gallium, arsenium, gallium, this is multicrystalline. We have indium, phosphorus, gallium, indium, phosphorus. And if you see this thin film, thickness is in nanometer. It is 10 nanometer. Gallium, arsenium thickness is very, very less, 10 nanometer. And it is on the substrate, germanium. Okay. And so structure you can see is very, very good. But problem is the arsenium. This is actually, it is toxic material. But of course, thickness is very, very low, 10 nanometer. So it is good, but we need 10 nanometer fabrication means you need very sophisticated instrument for manufacturing. This is the problem. And gallium, Ga, this is another problem. It's not so plenty, so expensive material. That's why when we need for the space application, when we have very less space, when we need very light, then we go for the this solar cell. And you can see for thin film, efficiency is very, very good. 29. Of course, area is very small. For the large scale, you can see 4%. Sorry, 18%. This is 4 centimeters square. Next is the this is the trend. This is the life of the these solar cells from the NREL. Then we have the chalcogenide based solar cells. So here we have the copper, indium, gallium, selenium, selenide based CIGS, very popular. Cadmium, tellurium. These are the thin films. Okay. So here, this is the structure you can see. Let me check the timing. I have more. I have 3 minutes. So here I have CIGS. Here you can see it's very, very good, 23%. When we go for the submodule, it is 665 centimeters square. It's very attractive, 19.8%. For the CDTE, 21%. For CJT, SSE, like that. Here you can see. So that CGSE, you can see very, very good. And this is the trend. Then we have quantum dot sensitized solar cell. Quantum dots are very, very small. It is in nanometer scale. It absorbs the light. It absorbs the light. And here, semiconductor is the TiO2. Semiconductor is TiO2. But TiO2 band gap is very, very high, 2.2 electron volt for the anatase phase. So that can't absorb the light. So naturally, we need some material which can absorb the light. So here, quantum dot, which is in nanoscale, in 1 nanometer, like that, 2 nanometer, 3 nanometer. So which absorbs the light. And this here we have the HTM, whole transfer material, spiro. And then we have P dot to collect the electron. And here we have the P dot SSS. So this here you can see to collect the holes, like that we have the structure. And this is the trend. At present, we have 18%. Still very, very good quantum dot cell. Then we have organic solar cells. The advantage of the organic solar cells, it is flexible and it is organic. So it is cheap also, economically easy. So this is the structure. And this case, you can see efficiency is nowadays very good, 15.2%. Of course, area is less, 1. But when we increased 19 centimeters square, it is approximately same. And when we increase further, it is 11.7%. It is equivalent to your amorphous-based solar cells. So this is the advantage. Then we have nowadays perovskite-based solar cells. This is the structure you can see. And for the perovskite-based solar cells, we use TiO2 to have the perovskite material, methyl, ammonium, lead iodide. But here PB is not good. It is toxic material. So people are trying to replace the PB by another material. I think I have now 5 minutes left. So I will try to finish as much as possible within 5 minutes. Then we have the we have HTM material to get the electron in holes. And then we have gold material, like that. This is the structure. And we have light from the bottom, from here side, this side. So here, these are at present, this is very, very popular in the research field. And efficiencies, you can see 23.7. And when you go for the mini module, 26 centimeters square, it's very, very high. But problem is for the perovskite based solar cell, the stability. People are still trying, facing problem to stabilize the efficiency. This is the basic problem. And till now, it has been reported 25.7 for a very small solar cell from the Korea UNIST Ulsan. And next, this is the trend you can see. And then I will talk about the sensitized solar cell. This is very, you can see it has so many advantages. It uses no toxic material. It uses low cost materials. It is ecologically as well as biologically benign. No expensive equipment for manufacturing, engineering into flexible slits, short payback time. For the when you go for the silicon-based solar cell or CDSE or any type of inorganic material-based solar cells, you have incident angle-based efficiency. Means the solar cell depends on the angle of incidence of your light. But when you have DSSC, dye-sensitized solar cell, you don't bother. It is free, okay? Doesn't matter. And when you have high temperature, the efficiency will be more, okay? And when we have diffuse condition, efficiency will be more. So these are the advantages of the dye-sensitized solar cell. And this is the structure you can see. Here we have electrolyte, maybe liquid or solid, which is the which has iodide triiodide redox material or cobalt-based redox material or copper-based redox material, which is sandwiched between the working electrode, which is made of dye-sensitized TiO2. As I told you earlier, TiO2 band gap energy is 2.2 electron volt, which is very high, which is not good to absorb the sunlight photon. So naturally, we need a dye. So dye function is to get excited from the HOMO to LUMO, give the electron to the current collector that passes through the current collector at the bottom side, which goes to the, then here we have the triiodide. That triiodide collects the electron and gets the into iodide, in the iodide. So this is the basic thing. So, and this is the mechanism as I told you earlier. And what is the role of electrolyte? So it regenerates dyes via the oxidation of iodide into triiodide at the working electrode. It reduces triiodide into iodide at the counter electrode, and it inhibits the back electron transfers, like recombination. We don't want any recombination, which is not good for any type of solar cells. So these are the liquid electrolytes, and we have at present 11.4% for this type of electrolytes. This is iodide triiodide based electrolytes. When we go for the cobalt based electrolytes, efficiency is better than this. Even we have 14%, 14.3%. So, but problem is these are liquid electrolytes. As Dr. Ansuman Dalvi told, we don't want liquid electrolyte. Why? Because we have so many problems. Reduction in long-term stability, high pressure at high temperature results in backage of sealing and leakage of solvent, as well as the manufacturing problem. So we don't want, okay? So here you can see, instead of using single dye, we are using several dyes to cover the spectral region. Okay, so here we have SM342, Y123, then it gave 12.7. If we have only 7 SM342, it is less than 10%. Like that, we have to increase by optimization the dyes. But in the for the research, for the lab, in lab we use single. For example, I'm using only N719 or Y123. So this is the mechanism. You can see we have several dyes. So it goes like this: electron from the up to here, TiO2. This is the LUMO level of the TiO2, and this is a HOMO level. So from the dye, it goes to TiO2. And this is the characteristic solar cell pattern. This is from the Kiej et al. And here you can see the efficiency. For the dye-sensitized solar cell, the highest reported value is 11.9. It is from the company Soud. And when we go for the mini module, which has 26 centimeters square, it is nearly 11%, good. And when we go for the mini submodule, it almost 400 centimeters square, it is less. And from the EPFL, they have reported 12.25%. So this is the values, and here this is the trend. So in our lab, we are using the solid polymer electrolytes to synthesize, to fabricate the solid solid state dye-sensitized solar cell. And these are the reported things people have done. And the blue color shows the what we have done in our lab here in Saudi Arabia. So these are the materials, and I'm not going to discuss this thing now. Here you can see it's very, very simple. We are using the blending of PEO and succinonitrile, polyethylene oxide and succinonitrile as a matrix, and then the iodide, triodide. For iodide, triodide, we are using iodine based material, and then iodide like that. But it has problem. It absorbs actually the sunlight at 430 nanometer. That's why now we have moved to the cobalt-based system, and this is very, very good. So here, conductivity measurement, conductivity should be equivalent to the liquid electrolyte. This is the target. So this is the conductivity measurement. And then temperature dependence, it should be stable in wide temperature range. So activation energy should be less than 0.3 electron volt. And then it should be amorphous. And then you can check by different ways, amorphosity by DSC also. And then it's stable, it should be thermally stable. And then we go for the solar cell fabrication. But here you can see efficiency. In my case, when I use PEO, efficiency is very, very less because of the interfacial problem. We don't have very good connectivity between the TiO2 dye and electrolyte. This is the problem. That's why when we use succinonitrile, it helps, but still you can see efficiency is not good. The problem is the interfacial connectivity. And these are the IPC spectra, is very, very good. You can see. Then we model it, this Nyquist plot, and then we get the resistance. Like that, we do some extra work. And now at the concluding section, I will show the confirmed solar cell efficiencies of the actual solar cells, terrestrial modules, and for different conditions. So this is non-concentrating. This is the actual solar cells, okay, in the market by different companies, Kaneka, Hanwha, China. This is Alta Devices, Solar Frontier, like that. So several companies. So here for the silicon-based solar cell, you can see 24.4%. Okay, can you see area? It's very, very big. Okay, for multi-class 20%. For the gallium arsenium, this 25%. For the CIGS CD-free, it is 19%. Thin film, 19%, the CDT. For the tandem cell, 12%. For the perovskite, 17.9%. For the organic solar cell, 8.7%. Okay. For the multi-junction, as I told you earlier, if we have multi junctions, if we have multi semiconductors according to the band gap, then we can collect the all wavelengths of the sunlight. Then we can increase the efficiency. So here you can see efficiency of the indium, gallium, phosphorus, upper section, middle section, gallium, arsenium, bottom section, indium, gallium, arsenium, and then between we have the tunneling layer, then we have 32.65%. So if we have multi-junction, here 3 junction, you can see is very, very high. Okay, it's very, very good. When we have CIGS 18.6%, like that, you can see it's very, very good. And when we have multi-junction, again, I showed you only for multi-junction. So here you can have 38.8%, 37.9%, 32.8%, like that. It's very, very impressive. So that's why, but making problem with the multi-junction is you need very expensive equipment. Manufacturing equipment are very, very expensive. That's why cost is very high. Area is less. The manufacturing, and also you have manufacturing problem. Can you see it is 1 centimeter square, 4 centimeters square, 1 centimeter, like that. Okay, so this is the problem. It is very, very expensive. That's why we are still on the silicon-based solar cell. And these are the other materials. Here you can see when we have gallium, this again 39.5%. And here I want to show you the concentrator. Now this is with the concentrator. So this shows the intensity, 1x, 2x. This is 61x. At the lab we do 1. But here this is 61. So we have concentrator. This is the type of concentrator. Here you can see this is very small, 4J, 4 junction cell. And here we have lens, Fresnel lens. So all are concentrating the sunlight into the our solar cell. So when we have like this condition, you can see efficiency is very, very high. When we have this condition, if the intensity is 665 times, then we have how much? 47.6%. So it is very, very expensive. As I told you, this is very impressive. But again, very, very impressive, but expensive. So you have to control. You have to then think how to manage. So this is the my thing. The concluding part. Now these are my collaborators, Professor Hyuri from Korea, Professor Idris Bedja, who brought me in Korea, in Saudi Arabia, Professor Nail, his collaborator from the UAE University, and I acknowledge the NPST as well as the UAE University for the funding our research projects, and I'm grateful to the organizers, to the listeners. And thank you so much. And really, because of Mohan, especially Mohan, actually, he told me, Gupta sir, can you present on the solar cell? So I tried my level best to give you about the glimpse on the silicon-based solar cells. And I learned actually. Thank you, Mohan, again and again.
वेलकम सर, आपको बहुत
really मोहन, मैं भी सीखा हूँ यार, बहुत सीखा हूँ मैं भी. I'm learning, frankly speaking, because see, we are not working on the silicon based solar cell, so we don't know much. But because of you, see, I made presentation file, just reading, learning why. So thank you so much.
We are learners, and I know मैं आपसे सीखा हूँ कैसे सीखना है. तो आप सीखते जा रहे हैं, मैं भी सीखते जा रहा हूँ साथ साथ में.
नहीं ऐसी मजा आता है.
तुरंत रिप्लाई किया मैंने, मैम को कहा कि भाई मैम प्लीज गुप्ता सर इज रेडी. और शायद आप ये से साइंस कॉलेज के एलुमनी भी है ना सर? आपने बीएससी वगैरह वहां से किया है क्या? साइंस कॉलेज रायपुर से? नहीं,
ना
अच्छा,
नहीं
थोड़ा सा ये कंफ्यूजन।
मैं वो राजनांदगांव
अच्छा,
राजनांद
yes,
से किया
हाँ,
दिग्विजय कॉलेज।
हाँ, दिग्विजय कॉलेज से।
हाँ,
ठीक,
दो जगह से था एक्चुअली। बेमेतरा से एक साल
yes,
बेमेतरा में थे, दूजे के ट्रांसफर हुआ नांदगांव में, सो नांदगांव मूव हुए। सो आई डिड फर्स्ट ईयर in Bemetara, previous final in Nandgaon, Digvijay College.
Sir, we have students from Digvijay College, Rajnandgaon also. So they are also
Wow.
a great opportunity for them also.
yes.
Question and answer. We have two students who want to ask some questions.
Yes.
Good afternoon, sir. And my question is it possible to make graphene-based solar cell?
Yes, why not? You can use graphene. Actually, people are using for the, instead of PT, you know, platinum is very expensive. So if we use graphene with the activated carbon, again, then we can increase the area of then we can increase the efficiency, as well as we can reduce the efficiency. We can reduce the cost. This is the advantages. And graphene we can use with the electrolyte also. So what will happen? Actually, see, our target is, of course, we are working on the electrolyte. When you are working for the batteries, for the supercapacitor, for the fuel cell, it should be pure ionic, no problem. Okay, it should be pure ionic. But for the solar cell, we don't bother about the ionic or electronic. If you have little electronic also, no problem. So this is the advantage. So we can use graphene in the electrolyte also.
Thank you, sir. Now,
Most
next.
welcome.
Good afternoon, sir. And my question is, what do you think about the future of solar cell in India? Is it bright or not? As India is a developing country, so the cost of manufacturing solar cell is very high. So how to reduce it?
If you see the silicon-based solar cell, in India, we have so many, but unfortunately, all shut down. None is working. Why? Because we have solar plants, we have cheap material from the China. Okay. So if we manufacture silicon ingots, if we manufacture everything in India, then it will be cheap.
Yes.
It will be cheap. Okay. If you are relying only on China, you can't do anything. Okay. So made in India, it should be made in India from A to Z. All components of the material of the solar cells must be from India. Then only you can reduce. And you must have the technology also. So you have to work on the technology also. When I was in Korea, South Korea, we were working for developing the technologies from A to Z. We should not rely on other countries. This is the basic requirement. Is it clear?
So UAE में आप लोग मतलब किसी पे रिलाय नहीं करते, खुद ही से पूरा A to Z.
आत्मनिर्भर बनना पड़ेगा. So we have to we have a big think station. We can think and we can work for this. So होता ये है कि हम छोटी-छोटी चीज जो है, चूंकि वहां से कम कास्ट मिलता है, तो ला करके फिर उसको यहाँ इंसेंबल कर लेते हैं और इंसेंबल करके काम चलाते हैं. उसके बाद फिर जब उसका मेंटेनेंस की बात आती है, देन गड़बड़ा जाता है, क्योंकि मेंटेनेंस जो है वो कर सकते हैं, टेक्नोलॉजी उनका है. अगर आपके पास सिस्टम है एंड यू कैन मेंटेन, then obviously the solar cell technology, and that this is India will have a bright future.
You can't believe while doing PhD, we were making furnaces, we were making our sample holders so many things in our lab only. And I'm doing here in Saudi Arabia same. I did the same thing in Korea. Okay, what I learned during my PhD, I'm doing the same thing in Korea, in Ethiopia, in even in USA also. I was doing, because my background is in such a way that I can make anything. I have now thin film, homemade furnace, homemade oven. I have the sample holder, क्या बोलते हैं उसको, spin coater, homemade spin coater.
Yes.
Everything homemade. I can make myself everything. I don't bother. Otherwise, it's very expensive.
Thank you, sir.
Most welcome.